Okay, hello and welcome to my webinar today on using raw engineering data in your simulation analysis. So essentially, the idea is that we would like to take realistic material property information and plug that into Solidworks simulation to get the most realistic results that you can get. Now, material is very important when it comes to simulation analysis. So, and the reason for this is because your geometry is only geometry. It's only a dumb solid. It's only made up of SolidWorks features until you add your material property. That's when it becomes real. That's when you get the mass of your geometry, the volume of your, well, the volume comes with the geometry. However, the mass and weight comes with your material property. And of course, how it reacts to external loads, such as pressure or forces. And also, depending on how you constrain the part, the material can play a very important aspect as to how the part deforms. Certain material, as you know, are stronger than others. So, and I'm sure as many of you have experienced while running your simulation analysis, you've come across a material which is not in the SolidWorks material database. Now, it is an extensive database, but in this day and age, there's material that comes out. There's a new material coming out every day. And we want to be using the best and the most affordable material that's suitable for our design, for our product development. So you might go out onto the internet and look for material properties. A lot of times these vendors that put out the material, especially nowadays, because they themselves have simulation analysis and physical testing physical testing facilities to put out material property, as they know how important it is. It's fairly easy to find material property in the internet. Few other ways that you can gather material properties is through textbooks. I've seen several textbooks that have put out stress strain curves for the more popular materials that's been used many times over the years. All right, so let's see. Someone just said the sound has been disabled. Let me see. Okay, let me just share this one more time. Okay, can everyone hear me now? Okay, all right. So I got a few yeses. Okay, very good. Thank you for the replies. Okay, so so of course, yes, you can go on to you can find material properties on textbooks. Now, I've actually gotten a certain level of success getting material properties from journals. Now, this is a really good source to get material properties because a lot of times newer journals are using new materials, and they probably have much better access to materials in the in the academia world. So I have also been able to capture material properties looking for just scouring the internet, Google Scholars, and finding journals, and using those properties as well. Another source to get your material properties is obviously the SolidWorks materials web portal. So this is a web portal that goes beyond the SolidWorks material database. However, you will require a license of Simulation Professional or Premium to be able to access this SolidWorks material web portal. So just to show some of you who have access to this license today and you're not aware of this, so within your material database, there is a very small link down here. Click here to access more material using the SolidWorks Material Web Portal. And this is the note that basically says you will need the SimPro or SimProfessional license. Say OK. And it brings up this web portal where you can specify a type of study and even the different types of material, metal, plastic, rubber, even a subclass of your material. And there's 4 different databases that it runs off, and you can pick all these different databases to look for those materials. So that's a really good way of looking for materials as well. So I'm going to go ahead and close this out. Go back to my PDF. And of course, as CAD Dimensions, we experience simulation. You know, we are working with several different customers that work with several different types of material, and a lot of times we get access to these materials, and we typically keep that in our database here. So if you come across a material that you really, you know, after going through the internet and textbooks and journals and the web portal, and you really still can't find your material properties, ask us, and we might be able to help you with that. And of course, last but not least is testing your raw materials. So this is probably the most concrete method to get your material properties. So you're not really depending on any internet search or textbooks or journals. You're basically taking your stock part, sending it to a material testing lab, and they would put together the material properties for you. Now, CAD Dimensions can also recommend a few companies that do this. We work very closely with a few companies that works with us, so they're very familiar with SolidWorks simulation. They would be able to create the SolidWorks simulation material data file for you, and all you really need to do is just upload it right into SolidWorks. So today I'm actually going to be focusing on this last option right here to show you how you might be able to do this yourself in your own facility, as you may have access to a few resources to be able to do this yourself in your testing lab or in your machine shop. Okay, so let's go to the next page. So as I had mentioned, a lot of this data can actually be extracted using a tensile stress machine. Now, I've actually visited many of our customer sites, and many of these engineering companies have one of these machines. Now, it's a very popular machine. It's been around for many years, and a lot of you probably have this in your facility or have access to this tensile stress machine. And using this machine, you can actually extract information that can then be transferred with a little bit of math and transferred into usable data to use within SolidWorks simulation. Now, some of you may ask, why would I go through the trouble of doing this when I can just go to MathWeb or look at the internet or look at some journals and just get the material properties and plug it into SolidWorks simulation? Well, I'm going to go to an example today where I do both, and we can see how when we run SolidWorks simulation analysis simply using hard numbers, so your yield stress, your tensile stress, your elastic modulus numbers, those constant numbers in your analysis, your results that you get is much higher than the results that you would get if you were to use actual data. All right, so with that said, let's jump right into SolidWorks. Before that, I just actually wanted to show you, I did mention the stress strain graph a few times. So websites such as MathWeb will not give you a stress strain graph. They will give you these numbers. They will basically give you a yield point or an ultimate strength. And you will be able to plug in these numbers into SolidWorks simulation. And basically what happens is there's basically some form of linearization going on there, where SolidWorks simulation is trying to create a curve as close as possible to those material properties you're putting in, but it's not really precise. As I had mentioned, it's linear. So you could be missing very important information in there. So being able to use a tensile stress machine, you'll be able to recreate this actual stress strain graph for your material right within SolidWorks simulation and run, and typically you would have to run a nonlinear analysis in this case, because what a nonlinear analysis will do is it will break your analysis down into smaller iterations, and it will take into account the change in stiffness due to stretching of your part. In addition to that, it will not linearize your results, and if you have any external loads, it will keep the external load normal to the face as opposed to normal to a global coordinate system, which is not very realistic, as you will see in my example here today. So right into SolidWorks. So what I have here is just a very simple part, and it is fixed right here in these two slots. So I'm going to show how it's fixed. So I simply just imagine if this part is slid into a railing, and it's maybe bolted down, or it has very tight tolerance, so it's pretty tight in place. So it's fixed, and there is a force being applied on that surface area right there, on this surface area right here, because and the reason why I picked this surface area is because typically a tensile stress machine has a tool which looks very much like this, and it sits right on that face right there. So I took that exact surface area and split that face to create the a focal point for the force, which is 400 pounds going in the X direction. Okay, so I'll just hide this constraints and external load. And so the mesh that I applied, clearly I have some mesh controls in there in the areas of some internal fillets that I have, and of course on the face that the force is being applied to. And I already pre-ran this analysis. However, it was fairly quick to run, but just for time's sake, I already pre-ran it. And then I look at my stress. The results that I get for my stress is very realistic. So that's really how it should look. And if I were to animate this, that's exactly how I would think my part reacts. Now, when I look at my displacement, again, obviously it's the same shape, but I'm starting to look at the numbers. So it's obviously 5.24 times 10 to the power of minus 3 inches. And if you have done this if you have experience using this, building parts like this in the past, or if you are familiar with this material, which is an aluminum alloy, T61, this number is starting to look not very realistic. And if you look at our displacement on true scale, it's obviously you can't really see it because of how small the number is. But I'm starting to think that this is not a very realistic type of results. So I did get a request to show the mesh, so I'll just quickly show the mesh before we continue on here. So this was the mesh that I used. As you can see, around the stress area was a little bit tighter, and of course in the inside fillets very tight as well. Okay. All right. So let's take a second here and take a look at our material properties. So very straightforward technique of putting in the material. As many of you know, red is a required material property for the type of analysis that you have chosen. In this case, it is static, linear static analysis. So I definitely have all the reds filled in. But again, being perhaps someone who have designed this before or familiar with the material, you might start to question the results that you're getting here. And this is where you can now reevaluate this analysis using a nonlinear analysis and using a stress strain graph. So before we jump into the nonlinear analysis, we need to evaluate or need to talk a little bit more about how we can gather this raw data. So just imagine if you have a stock part like this, and it really doesn't even have to be machined like this. So maybe even if it's an L shape, and you put it in your tensile stress machine, and you run a quick test. Now when you run a quick test, the tensile stress machine will shoot out information which can then be read in Excel. So let me show you an example of a raw data set in Excel. So everything in blue here was basically spat out by the tensile stress machine. So the time from when the stress was applied, the external load was applied, to the point where it has deformed and the tensile stress machine piece that was causing that external load has slid off the part. So you can see that if we scroll all the way to the bottom, we have was roughly about 15 seconds. It will tell us the extension. So in this case, the extension is how much the tensile stress machine has moved in the vertical direction. So that may not be the engineering strain at this point. So we need to think about that for a second, and I'll talk about how we were able to transfer this extension into an engineering strain. Of course, the load will also be applied. So we are trying to work our way up to 400 pounds. And you will see that over 15 seconds, the load is accumulating to about, well, in this case, is much higher than 400 pounds. And really the reason why I did not use 400 pounds in our linear stress analysis is because the part essentially buckled. So that would be a really good showing that linear stress analysis might not be a good type of analysis for that test. And so once we have our load, I was able to calculate the engineering stress. So engineering stress here shouldn't have been in the blue. The engineering stress was essentially calculated using the load and the surface area where the load was applied onto. So having calculated the engineering stress, that will come back into play when I transfer that into a true stress, which is what is required for Solidworks simulation. Now, the mathematical part of this is to get to your engineering strain. To your true strain. Now, the extension of the part is really this. So if you use our general right triangle rule, it's A. That is what the tensile stress machine is throwing out. The engineering strain that we are looking for is the extension of material for your C. Now we know what B is. B is essentially what the part is at rest. C is when it has been extended. So if you look back here, I have A as 3, 3, and C is the extension of this geometry right here. So this is A right here, and C is the length that I had gotten from SolidWorks simulation of how much it has extended over this period of time. This obviously can just be calculated using the general right triangle rule. Using A and C, I was able to calculate the delta L, which is the difference between the length at rest and the extended length, delta L. And then using delta L, I was able to calculate the engineering strain right here. So it basically was the delta L over the extended length. That gave me the engineering strain. And now we already have our engineering strain and our engineering stress. Within SolidWorks simulation, to be able to create your stress strain graph, it only uses true strain and true stress. Now this is the easy part. I simply went to Google and I was able to find an equation that translates over engineering strain and engineering stress and strain to true stress and strain. So true strain is the natural logarithm of engineering strain plus 1, and the true stress is the exponential of true strain times the engineering stress. Okay, so these two data right here is what you will input into SolidWorks simulation to create your stress strain graph. So let's take a look at that. So within the nonlinear analysis, if you look at our edit material, now within nonlinear analysis, you'll be able to select a material type. And in this case, I picked nonlinear elastic, which is the most realistic type of model, material model that you can use to run your analysis. And in terms of property, all it really requires for hard numbers is just these numbers right here: tensile strength, mass density. I really didn't even need the thermal expansion coefficient because I had no thermal effects on this analysis, but I had that number, so I put it in, and your Poisson's ratio. Everything else comes directly from your stress strain curve. So using, when I selected stress strain curve, brings me to this table where I simply copied and paste all that information, all that data from Excel into this table. So just right click, copy and paste because they are cells, so you'll be able to transfer directly. And this created this graph for me. Now you will see that this graph actually stops at ultimate strength. So I didn't really take into account the plasticity of this part, and I don't really need to because this is an aluminum part, which I really just want to see how it will deform up to the ultimate strength point. Exit this, and that's really all required for material. And let's take a look at our results. So the mesh is still the same from before, not much has changed. And I am getting a few questions here, so just hold on and we will answer the questions towards the end of this webinar. And what we'll do is we'll jump right into displacement. So give it a second here. There's a lot more information for nonlinear, so it takes a little bit of time to read in all that data. So one I guess question that I got, or not question, or comment that I got was the force calculation it could be wrong because of how the force is applied over the area would only work on tensile loading conditions, and the part is bending, and the stress would obviously change as the part is bending. That is absolutely correct. However, the results that I've gotten for the stress calculation, and I really have to kind of recheck this. I did this a while ago for the engineering stress. In terms of loading, this came directly from the tensile stress machine, and the extension also came directly from the tensile stress machine. So I did really, I'm not really making any assumptions here for the engineering stress. I did have some calculations here, but it's sort of been removed now, so I can probably address that later. However, again, this came directly from the tensile stress machine. Okay. So as we can see here, our results has changed significantly. So in the previous analysis that we did, the displacement that we got was significantly smaller. Now this right here looks much more realistic in terms of displacement. And again, this is obviously an exaggerated view. So what I'll do here is, it is actually true scale. So we should be good here. And we can also change this to results and displacement. So again, just give it a second here. It's just reading in the results. All right, as this is as the results are reading in, let's answer more questions. Which model to use for nonlinear material like rubber and PTFE? So there is a few different model types underneath that in the material, the material property window. There's hyperelastic, there's non-elastic, there's plasticity. I believe there's 6 different model types. So we can actually look and see. So depending, so if your material, so there are some materials that can react, hyperelastic, and in that case, obviously you would want to pick a hyperelastic model type. So essentially, what the question was referring to is, what model type would you pick? So under plasticity, there's 3 types of plasticity: von Mises, Tresca, and Drucker-Prager. I do have more information on what is suitable for the type of plastic that you have. So if you are testing a plastic material and you're not sure which one, please reach out to us and we'll be able to point you in the right direction. Same as the hyperelastic, viscoelastic, and nitinol material. So again, if you are testing a type of material which is suitable for nonlinear, just reach out to us and we can probably point you in the right direction for model type. Another question received is, can you please repeat how you calculated A and B again? So A is basically the length at rest of this part. Now, as this part is being deformed, it is extending. So as it extends, it gets longer. So using the right triangle rule, right? So if it's 0.33, go back to this. So if this is so if we have this number right here, it's 0.33, and we have this number from the tensile stress machine, which is the extension right here. We are able to use this equation to calculate this length right here, which is C. Okay. So once we calculate C, you can see that I actually have that equation up here. It's E square plus B square, and the entire thing is it's the root square of the entire thing. And so that is the extension. And now we want to know the difference in extension, so how much it has extended over 0.33, which is why I created delta L, which is essentially C minus A. And then using delta L, I calculated the engineering strain, because engineering strain is the change in length. So it's the delta L. Well, this is delta L, so it's the delta of delta L, which is it's the ratio of delta L in reference to the length, the extended length. So that will be G divided by F. Okay. So again, if anybody wants access to this Excel file, please again reach out to me, and I'll be more than happy to share it with you. Okay, so let's go ahead and take a look at some results that we've gotten from this analysis. So just giving it a second to think here. Okay, so as the results is coming up, let's go ahead and answer more questions. Does this method give generalized curves, or are the curves dependent on the geometry and loading, only useful for the part in question? So the the curves that was created using the tensile stress machine is obviously more suitable for the type of geometry that you're going to be testing in your simulated environment. So obviously the thickness of your part will play a huge part in terms of how it will deform. Now with that said, you are getting much closer to actual results if you are getting raw data from your tensile stress machine and using it on similar geometry. So it doesn't have to be exact geometry. So in this case, in this analysis, the raw data was actually taken using a part which was pre-machined. So it didn't really have any of these slots in it. It didn't have this cutout in the back. It didn't have this cutout right here. All it really had was it had the L shape. So yes, it would make sense maybe for you to machine it down to its maybe its minimum thickness, and then putting it on your tensile stress machine, gathering those results, putting it in Solidworks simulation will then allowing you to make appropriate changes, or even being able to test the different boundary conditions required to for the part, trying to figure out the right factor of safety for the part, and run fatigue analysis on the part as well. Okay, so another question here. Okay, so the question is, can you explain more about the difference when using nonlinear materials? You mentioned that the stress will remain in the plane of the surface versus the global coordinate. Okay, great question. So now imagine if you have, if this stress was not applied on a focal point, but it was applied directly on the whole face. Uh, the reaction that you would get is this wall would probably bend up this way. Now, if you look at my arrow of my mouse, a linear stress analysis will react this way. It will go and it will just go straight up. Now, this does not follow the direction of how the face is bending when the stress is being applied. Now, let's say if your part is bending in this direction. In a linear analysis, your stress will follow that wall. It will stay normal to the wall as it deforms. That makes a huge difference. In a linear static analysis, the force is instantaneous. So basically the force is applied, and if it's applied in the normal direction, vertical, or basically normal to the face, it's just going to go in this direction. And sometimes you can get results where it's deforming more than it should, or it's not deforming enough because the part has deformed significantly and the force has completely bypassed it. Okay, so you probably can't see my mouse apparently from what is being said. Oh, okay, all right. So sorry about that. Seems like the screen was jammed there for a second. All right, so let's just kind of explain this again quickly, and then we can wrap this up. If your wall right here is bending in this direction, your your force will follow the face as it bends, because the analysis is broken down into smaller iterations. So imagine one analysis broken down into 1,000 smaller analysis. In a linear static analysis, it is a single analysis where if your force is normal to the face, it will remain in that direction. It will never follow the direction of the face. So as the face deforms up like this, as you can see this face right here, as it deforms here, the force will not follow this. It will simply go straight. It's an instantaneous force. And perhaps if you have more questions about this, I have some examples that I can show you offline as well. Any other questions before we wrap this up? I do have one more thing to show you. It is a video of how this analysis looks in a nonlinear environment. So you can see that the deformation of the part is more defined here when we are doing it in small iterations, and the material is defined much better, more realistically. All right, so that's really all I wanted to cover today for this webinar. I wanted to keep it within the 40-minute range. Any final questions before we wrap this up? I just wanted to again kind of show you this screen right here. What we looked at today was running a static analysis versus running a nonlinear analysis, where you can apply nonlinear material properties, and also having access to the material web portal will be a part of Simulation Professional and Simulation Premium. So again, if right now I'm not getting any more questions, so if you do think of a question maybe later today or tomorrow, please just send me an email or give us a call and ask for me, and we can speak further. All right, thank you everyone. Thank you for joining me, and I hope you have a great rest of the day.
Don't forget to check us out on YouTube, Twitter, Facebook, and our blog for more great content by clicking on the links in the description below.